Good morning, everyone. So we continue the topic of properties of fluids. Yesterday, we were in the middle of viscosity. So we had done some questions on viscosity. So I'll do one more question. Where a similar question had come in the past. A disk of radius r. So we can well imagine there's a disk here, and disk can rotate about a vertical axis, and it is kept on a flat surface. So this is a disk of radius r. This what you see is a disk here, and this is the ground surface here, and in between the disk and the ground there's a thin layer of liquid here, and it could be a passage, and this kind of thing can happen in many actual production activity. There's something which is set into rotation, and when it is set into rotation, if fluid has viscous property, it has like frictional kind of property, it will offer resistance to motion of the disk here, and you need certain torque to keep the disk rotating. So if we want to rotate this disk at angular velocity omega, thickness of the fluid is T. This is thickness of the fluid here, and this radius is R, and we are rotating with angular velocity omega. What is the torque required? If that's what we need to calculate here. And as you know, as the disk rotates, just look at the cross section here. So different part of the disk will have different velocity, and velocity will vary from distance r here. So our formula takes a constant velocity. So we need to take the disk in terms of several concentric rings. So first we visualize, if you view from the top, this is like the top view. So this is the whole disk here. I'm not looking at the whole disk first. Let's first find out what is the torque on a ring. A ring of radius r. So this has a ring has a radius r here, and its width is dr. It's a flat ring. The bottom surface is flat. And to calculate the torque here, I'm not even taking the ring first. Let's take a small part of the ring. Which part of the ring are we taking? This is the part of the ring we are taking here. And this makes an angle d theta at the center. So if I look at the ring here, where's the ring part here? This is the part of the ring. If we look at the cross section is here. You know, this, it will have a flat bottom surface. And length of this, if the angle is d theta, this will be like a flat rectangular plate here. And flat rectangular plate width is dr, length is r d theta. At this instance, this is equivalent to a flat plate of area, width is dr, and length is r d theta. It is, sorry, small r d theta, and it is moving with a velocity equal to r omega. I can find out what is the force which will act here. Let's apply our viscosity formula here. Force on the small element, df, it is eta times area. Which area do we take? Area of the plate which is in contact with the liquid. What is the area which is in area of the plate which is in contact with the liquid? We have just mentioned here. That's the area of the plate which is in contact with the liquid. R d theta is the length, and dr is the width. It's like a rectangular plate. And what is the velocity, and what we multiply? Velocity gradient here. So top surface of the liquid, if I look at here, the top surface here of the liquid will have a velocity r omega, and bottom surface a velocity 0. So how is the velocity gradient here? This velocity is varying in the vertical direction, and delta v is r omega, and delta y is t. So this becomes the force. So if it is rotating like this, it will experience a force like this. Df is the force acting on the small element. And when there's a force here, we are interested in torque. We can calculate torque also. Torque will be equal to this force multiplied by the distance from the axis of rotation. So whole term df, if I multiply by r, it becomes torque on the small element. And you notice here, if I take all elements one by one, all elements torque is in the same direction. If I look at the torque, which direction the torque is acting? If I look from the top, torque is acting in the anti-clockwise sense. So since even though the torque is vector quantity, I can add it up. So when I add up this whole term here, this is torque in the small element. If I cover all the elements which are part of the circle, the only variable, rest all are same. Okay, width dr remains same. Only thing changing when you add it up is summation of d theta. Summation of d theta, that's become 2 pi. That's a summation of torque on the ring. So I replaced d theta with 2 pi, and that becomes torque on the ring. And if I have to add torque on all the rings, which are several concentric rings, so here I'll integrate with from 0 to capital R. So when I integrate, that becomes torque, is a torque on the disk is sum of torque on all the rings as all are in the same direction. I get the value of torque. Okay, next up, the one more application of viscosity is Stokes law. In Stokes law, see, first of all, what does Stokes law give you? Stokes law tells you the frictional force, which in case of liquid we call as viscous force. What is the viscous force? A spherical object moving in a viscous. What is the viscous force? A spherical object. So this is only for a spherical shape object moving in viscous liquid, and the force which will act on the object, spherical object, it depends on velocity. If it is moving with velocity v relative to the medium, the force is 6 pi eta r. That's the force. What we notice here, which direction will the force act? It is will act opposite to direction of motion. So if object is spherical object moving downwards, force will act upwards. This proportion velocity. If force velocity becomes double, force will become double. And if it is not moving, well, force becomes zero. It is proportional to velocity, opposite to direction velocity. And if object is moving up, it will act downwards. If object moving down, it will act upwards. 6 pi eta r. That's all. So, and rest all application is simple laws of motion. And what we keep in mind, opposite to direction of velocity, it will act, and it will be proportional to velocity. Velocity doubles, this also doubles. Velocity becomes half, this also becomes half. So let's say, let's take understand here. This is something, we have a large vessel of water or any fluid here, and if you have a small metal ball will have density greater than water, so it will sink. So as soon as we release, let's try and understand what kind of motion we'll have, and we'll analyze based on this additional force which comes into picture called viscous force. If a spherical mass released from rest in viscous liquid, it will have initial downward acceleration. Why it will have downward acceleration? It will have a net downward force acting equal to weight minus force of buoyancy. Force of buoyancy also written negative. Rather than writing weight is downward, force is upward. So I have written the net downward force is apparent weight here, apparent weight or effective weight. I will use the term effective weight here. Effective weight is weight minus force of buoyancy. And as it moves, this weight doesn't change, force of buoyancy doesn't change. It remains constant. So initially, this is net force acting. This divided by mass, it will have a downward acceleration. If you have to write a net force is equal to Vs minus Vl, V into G. So this becomes weight, and this becomes weight of the liquid force of buoyancy, and divided by mass, ρs into V. So we get this net, you can easily find downward acceleration. What happens here, as soon as we release, the velocity is zero, this is how the force is. And where is the viscous force right now? The velocity is zero, viscous force also zero. But as it acquires velocity, let's see, as the velocity increases, viscous force also start increasing. And how would, see, Stokes law is just laws of motion. So now what happens little time later, it has acquired some velocity v. And one more force is developed, it is viscous force. And velocity is downward, viscous force will act in the upward direction. Now we find the net force will decrease. Earlier, this was the net force. Opposite direction forces started acting. So net downward force decreases, hence the acceleration also will decrease. So velocity will increases, viscous force will increase, and acceleration will gradually decrease. So it will still accelerate, but at a lower rate. And as this, what will happen? Slowly this force will keep increasing, this downward becomes same. So downward net weight, effective weight is constant, because opposing force is increasing. If it keeps increasing at some time, both will become equal. So what happens at particular velocity? So as velocity increases, this will increase, and particular value of v, this force and this force become equal, net force will become zero. And when at velocity, when this happens, velocity at which net force becomes zero, it's called terminal velocity. We'll understand why it is called terminal velocity. So here, started from zero, acquired some velocity, kept on increasing. And here it has come to Vt, terminal velocity. And what we find at terminal velocity, this downward force effective weight is equal and opposite to viscous force. And here the net force has become zero. If net has become zero, what will happen to velocity? If net force is zero, velocity will remain constant. So if at this time net force has just become zero, if I see little later also, when it achieves terminal velocity, acceleration is zero, or velocity remains constant. So little time later also you'll find there's no change. Afterwards, it will keep moving the constant velocity, no change in forces, no change in velocity. It will be in a steady state, which is called terminal velocity. So terminal velocity, net force is zero. That's all. Viscous force becomes equal and opposite to effective force. And at terminal velocity, if I have to write the equation here, I equate this value to this value here. What is this value? 6 pi eta rb. 6 pi eta rb, and which we had at terminal velocity. And that has to be equal to W by weight minus FB. weight minus FB, I can write rho s minus rho L into Vg. And if at all we have to write in terms of radius of a sphere, we can write in terms of radius also. One r term gets cancelled. What we notice, terminal velocity is proportional to r square, and it is proportional to 1 by eta. So basically, larger the sphere is, if I drop one sphere of r radius r, and I drop another same material, same iron ball. If I have another iron ball of radius 2r, it will have a terminal velocity. If it has a terminal velocity v, it will have a terminal velocity of 4b. That's what this relationship says. Well, the terminal velocity is proportional to r square. The same material, same liquid, same combination material liquid. If the dimension of a spherical object is changed, as terminal velocity also will, it will become varies a square. Okay, okay. Let's continue here. And if object is falling in air, is the viscous force applicable? Yes, air also viscous force is applicable. Force of but in case of air, force of buoyancy becomes negligible. That's the only difference in case of air and liquid here. But effective weight will be equal to the actually weight itself. At terminal velocity, again viscous force becomes equal to weight of the object, and that's why the raindrop. You would see the raindrop also when it falls. You see the velocity; it remains constant. It doesn't accelerate. Why? Because it is falling from a large height, and because by the time it reaches, after some time, before it hits the ground, it acquires a terminal velocity. And what will happen in case of simple question if I ask, if at half the terminal velocity, what will be the acceleration of any object falling in air? When terminal velocity is half, see basically a terminal velocity, if this is the weight here, and this will be the force of buoyancy, equal and opposite. Sorry, this will be viscous force. This will be a terminal velocity. What happens if object is at half the terminal velocity? At half the terminal velocity, weight remains same, mg. But what will happen? Viscous force will become half. So this viscous force Fv will be equal to W by 2. So net weight is W by 2. This acceleration will be equal to G by 2. Just to understand what happens in case of air. And if object is given a velocity greater than terminal velocity, then what will happen? See, finally, if it is having velocity greater than terminal velocity. So let's see what we mean by terminal velocity. So for some reason, we can project an object if it is moving greater than terminal velocity in air or energy medium. So this is effective weight which is acting downwards. And let's say it is given a velocity in the downward direction, which is equal to 2 times terminal velocity. If it is 2 times terminal velocity, at terminal velocity, viscous force is equal to effective weight. At twice the terminal velocity, viscous force become twice as much. So what is the viscous force opposite to directional velocity? It will become twice the effective weight here. Effective weight is weight minus force of buoyancy. So in this case, what will happen? If this is more, it will have net force acting in the upward direction opposite to velocity. It will slow down. So if it is given a velocity greater than the terminal velocity, again it will slow down and finally will come to terminal velocity. So if I have to draw a graph here, I haven't drawn here, I can quickly draw a graph here. So how would velocity vary with time? So if this is velocity and this is time. So if object starts from rest, it will have a motion. If it is falling in a liquid, it will have more velocity, something like this. What we understand here, and finally what will happen, and what we notice here, after some time, velocity becomes almost constant, and this velocity is terminal velocity. This is how the velocity of an spherical object falling in viscous liquid will vary. And you notice here the slope is high here. The slope is acceleration. Gradually, acceleration will keep decreasing. That's what we discussed. And what will happen if we give initial velocity which is equal to terminal velocity? If we give initial velocity equal to terminal velocity, it will move like this. If we give velocity greater than terminal velocity, even then also it will happen. It will keep slowing down, and finally it will come to terminal velocity. It doesn't matter what the initial velocity is. If the depth of liquid is sufficient, any object finally it starts moving in a steady state with the terminal velocity when that force becomes zero. Let's take some example here. The ball rises to surface at constant velocity. So how would ball rise? If you want to imagine that one, take a plastic ball, put it to the bottom of a bucket and just leave the ball. What will happen? The ball will move upwards. It moves upwards because that force is acting in the upward direction. Force of buoyancy is greater than its weight. So okay, so what is given? A ball rises to surface at a constant velocity in liquid. its density is 4 times greater than that of the material of the ball. So if density is 4 times, it means force of buoyancy also will be 4 times the weight. That's what will happen. If density of the liquid is 4 times, then the ball here, force of buoyancy also will be 4 times because volumes are equal, submerged volumes are equal. So in this case, ratio of force of friction acting on the rising ball and its weight. So let's understand here what will happen. So which direction it is rising? So if I have to visualize a figure, what is happening in this case? It is moving at a constant velocity. It means it is moving at terminal velocity. Which direction? Upward direction. If it is moving in the upward direction, three forces are acting. But what are three forces here? Weight is acting downwards. And force of buoyancy is acting in the upward direction always. Weight and FB, there's no doubt at all. And this weight is equal to rho S into Vg. And FB is equal to rho L into Vg. And since the density is 4 times, FB is 4 times. So whatever weight is there, 4 times that weight is acting here. And it is moving at terminal velocity, upward direction, hence viscous force will act in the downward direction. And net force has to become 0. So if this W, this is 4W, this has to be equal to 3W. Very simply, we can arrive at clearly, force of buoyancy has to be 4 times the weight. And at terminal velocity, viscous force has to be equal to 3 times the weight of the object. And that's why the net force becomes 0. Nothing extra. We have just done equated all the forces in vertical direction to be 0. What will happen next part? What will be acceleration of the ball when it is moving up at half the terminal velocity? So what has changed here? So before it's at terminal velocities, at some point of time, it might be traveling at half the velocity. When it is traveling at half the velocity, this force will not change. This force will not change. Only this force will change. At terminal velocity, this force was equal to 3W. When speed is made half, this force also will become half. This force is proportional to velocity. At half the terminal velocity, Fv dash will become equal to, it was 3 times the weight, it becomes 3 by 2 times of the weight. Since it is proportional to velocity, and direction has not changed, the direction of motion also has not changed. So friend, what is the net upward force in that case? Net upward force will be equal to Fb minus the weight minus the Fv. So if you write all this term, net upward force is equal to 3 by 2 weight, or it you can write as 3 by 2 mg. And if it is 3 by 2 mg, its acceleration will be equal to 3g by 2. So when it is having that velocity, it will have a which direction the acceleration will be when it is traveling half the velocity, and Fb is greater. Fb is the sign is positive. It will have upward acceleration of 3g by 2. If I continue here, what happens? So suppose this is a plastic ball, a plastic bullet, and you have plastic gun. So if you give last part here, what will be the acceleration of the ball when it is moving downwards at half the terminal velocity? Now, which direction this motion is? Let's understand. How do we get that velocity? Velocity is downward direction. Viscous force will act in the upward direction. And since the at terminal velocity viscous force was Tw, half the terminal force viscous force will be equal to 3W by 2. That's a viscous force which is acting. Force of buoyancy and weight will not change. This is weight and this is equal to 4W. So these are the forces acting. If I fire a plastic bullet inside water tank here or any liquid tank at half the terminal velocity, what will happen? This is how the forces are acting. And let me find out what the acceleration will be. Half the terminal velocity. What are the net forces? 4W plus 5.5W minus W. It will be equal to 4.5W here. So net upward force is 9W by 2. Plus acceleration will equal 9g by 3. Very quickly it will slow down. It will slow down very drastically. There's a huge retarding acceleration. Velocity downward, net force is upward. It will slow down very quickly and then will start going up. So basically, this just 2 points we are stressing on. Force of viscous force acts opposite to direction of velocity, and it is proportional to velocity. And at terminal velocity, net force becomes 0. Okay, and let's look at one more question just to understand this point well. A small steel ball falls through syrup at constant speed of 1 meter per second. So this is terminal velocity. Net force is 0. And if the steel ball is pulled upwards with force equal to twice its effective weight, how fast will it have to move after a long time? How fast it will move after a long time? So basically, after a long time, basically it means only terminal velocity. So when this extra force is applied, in that case, it will have a different value of terminal velocity. What will be the terminal velocity if an external force is applied equal to twice its effective weight? Whenever we talk of effective weight is net of these two. So let's understand this part. Is this falling true? If it is falling means what are the forces acting? The weight minus force of buoyancy, downward direction. And this is nothing but effective weight here. We had used the term effective weight here. And it is moving the speed of 1 meter per second at 1 meter per second. So what is the FE here? Net force has to be zero. It's given here moving the constant speed. Net force is zero. It means viscous force also is equal to effective weight. Viscous force is equal to effective at what velocity? At velocity of 1 meter per second. Now what happens? Now there's some change here. At terminal velocity 1 effective weight. So FV or viscous force is equal to effective weight. Now under external upward force, again an external upward force, again we are calculating terminal speed. Net force has to be zero. So what is the net upward force? Net upward force is twice F minus FB. This F minus FB was already still acting. This other force applied. And in this case, which direction it is moving in the upward direction? This net force applied is in the upward direction, twice that much. So it will have upward motion. And hence the viscous force will act in the downward direction. This is the case given. And in terminal velocity, it has achieved a terminal velocity after a long time. I need to calculate here upward force. What will be the velocity? This V we need to find out. Let's see how do we find out V here. So net force has to be zero. So if net force has to be zero, what has to be FV here? If this is the effective weight, twice the effective weight, it means this also has to be effective weight. So here also viscous force is equal to effective weight. And at a velocity 1 meter per second, viscous force was equal to effective weight. So here also velocity has to be same. It has to be upward velocity of 1 meter per second. It will move with upward velocity of 1 meter per second after long time if we apply a force equal to twice the effective weight. Okay. Okay, now take a, this was based on Stokes law, which assumes viscous force to be proportional to velocity. Let's take a hypothetical case, and which may happen in some certain cases. A spherical ball of volume V is made of material with density rho 1. So material density of the ball is rho 1. It is falling through a liquid of density rho 2. And rho 2 has to be smaller than rho 1, then only you will have a downward acceleration. So a ball is falling in a liquid of a lower density. So its weight is greater than force of buoyancy. Assume the liquid applies a viscous force on the ball that is proportional to square of the speed. Unlike your Stokes law, viscous force is equal to, if it is proportional, K is the constant of proportion, viscous force is K times V square. In that case, what will be the terminal speed of the ball? So this only needs concept of terminal speed. And what happens at terminal speed? At terminal speed, velocity remains constant, acceleration is zero, net force equal to zero. So let me draw which forces will act. It has a downward velocity. Viscous force has to act in the upward direction. And net downward force is weight minus force of buoyancy. This force clearly it is given here. So this is how it will look like. All has to happen. Net force has to be zero. So we need to find and what is the net force. Just equate the terminal velocity. Net force is equal to zero. So if I write upward as positive, Fv minus W, so I could have written as maybe Fb I could have drawn upwards also, it doesn't make a difference. Fv minus weight minus Fb, F minus effective weight is equal to zero. I will just substitute all the values, easily get an answer. What is viscous force here? And velocity is equal to terminal velocity. So K into V square, in place of V I have substituted terminal velocity square, is equal to weight. Weight is density into volume into G, density of solid. And force of buoyancy, density of the liquid, rho 1 minus rho 2 into Vg. I get terminal velocity. Okay, and based on this viscous effect, there's one more thing called Poil's formula. And Poil's formula, it is not given in NCERT book. So still there's some degree of uncertainties there or not there. But this you cannot derive because derivation is long and tedious is not useful also. So in terms of understanding Poil's law, all we need to understand is basic formula and its use. And this basic formula you need to memorize. This also one of those formula. You should keep it memorized at least just before the exam. You should memorize and revise and memorize here. So what does it tell you? Basically, when the see in case of Bernoulli's law, if a liquid is flowing in a horizontal pipe and area of cross section is constant, so if I drill a hole and put two pipes here, both the places, if it is there's no loss of energy, liquid would have risen to the same height. The pressure would have been same at both the points here. That's what Bernoulli's law, when there's no loss here there's no loss of pressure head. See, first of all, this law is for a pipe of uniform cross section and horizontal pipe. This law is for what? A is constant. Area of cross section not varying. And this is applicable. And second thing, what it says, it is constant and pipe is horizontal. If area is constant and it is not is horizontal. So if area is constant, basically velocity is constant. That's what it means. And pipe is horizontal means H is constant here. So if there was no loss of energy, the pressure also would have been constant here. If liquid is viscous, there has to be some loss of energy. And if loss of energy, it cannot be in terms of velocity. Velocity has to remain same because of continuity. This is steady state. And pipe is horizontal, this cannot change. Only the pressure energy will change. So as the liquid flows here, if I put point A here, and here I find liquid rises to height h1. Another point B, which is a separated distance, it rises to height h2 here. And h2 in the direction of flow, the level will fall. That's what happens in case of rivers also. River flows from mountains to the sea, continuously losing potential energy, and loss of potential energy makes the flow possible. So here also, so there's a part is delta H here. So if I this at H1 minus 2, so delta P, pressure difference is equal to rho G into delta H. So pressure A minus pressure at B is equal to rho G delta H, and we can call this is a loss of energy per unit volume. So as in case of charge flow, there is a loss of energy. Similar thing happens in case of charge flow also. There is a loss of electrical potential energy. Here loss is in form of pressure energy, energy per unit volume. There we call of energy per unit charge. That's a voltage. Okay. Just a second. Okay, I think Jamshed sir is calling us. Okay, so we'll continue from here. So as the charge flow, so this is what happens. So let's write the equation here. So let's see and try and understand here. This is the background I have given. And what we know here, so when the liquid flows, what is the Q term here? Volume flow rate. So Q term indicates PV, rate at which liquid is flowing in the pipe. We call it flow rate. So flow rate is related to this P. P is the loss of pressure head. So this is the loss of indicates loss of pressure. So when the liquid flows in a pipe having a flow rate of Q, if 2 points are length of the pipe is L, radius of pipe is R, viscosity of the liquid is eta, over a length loss of pressure will be P. So P indicate loss of pressure or drop of pressure. And what does this indicate here? This is something is okay. These are the quantities which are related. I hope I'll repeat all this point again. What is Q here? Flow rate. Flow rate is equal to nothing but A into V. So it flow rate, what is the unit of flow rate? Meter cube per second in SI unit. Well, liquid flow rate, basically what it says, if same, if a flow rate becomes double, if you start flowing more water, start flowing from the pipe, what will happen? It will need more loss of pressure. Pressure loss will also become double. And it says the length of the pipe also. If I double the length of pipe, suppose I'll come to some question also, you'll understand that also. So these are the terms which are related. All we need to know what those terms are: flow rate, pressure loss, radius of the pipe, viscosity of the liquid, length across which pressure loss is taking place. P by L I can also call as pressure gradient, rate at which pressure is getting lost. P by L is called, it can be called as pressure gradient. So let's see in this case. So let's try and understand, apply in this case. And I'll just do one question. And if you pay attention, just one question is enough because this simple application of formula, nothing more. So volume V, so volume V of viscous liquid is flowing per unit time. So V is nothing but equal to Q flow rate. And due time, and pressure head is delta P. We can understand pressure head is delta P along a pipe of diameter D. Diameter of pipe is given, length L is given. So in this case also, what is pressure head? Just imagine, you could have all seen that one. Just imagine there are two tanks here. You can imagine two large tanks with difference in water level of delta H. They're connected with pipe. So I have one tank here, and which has water up to certain height. And there's another tank at some more distance, and this has water at a lower height. You know, we can transfer water, connect these 2 points. This is similar to, if you notice, there are a number of ways you can think similarity. It is like connecting a higher temperature object with low temperature object. So when I connect across these two tanks with the pipe here, so first of all, what makes the flow possible? Flow is possible because of water height difference. If water height difference is h, so delta P, pressure difference between two, is rho g. That's the pressure difference here between the two tanks here, which is constant here. But when I connect this pipe here, I can connect a pipe of length L of diameter D. I can connect that also. If I have at home one pipe of length L and diameter D, I connect, some water will flow at a certain rate at this instance. What if I don't have a pipe of diameter D? I have four pipes, each of diameter D by 2. The diameter is half of that, length is twice as much. So I can call this pipe also, it need not be a straight pipe. If it is connected like this, if four pipes are connected, if this is transferring at a rate of Q1, what will be the rate at which water will flow from tank of higher head to lower head? What is delta P, which is making the flow possible? GH, water head difference. Over what length? This length or this pressure energy is lost over the length of the pipe here. Rest all is application of formula. Let's read that one. So this is something to give intuitive head, or in terms of figure, I can show it like this. This is what is happening. Length is L, diameter is D here. Okay. And if I write the equation here, very simply write the equation: flow rate Q is equal to rho into P. Pressure is not changing. Diameter, radius is D by 2 raised to power 4, 8 eta L, length of the pipe. Second case, what is happening? Now I have drawn only one pipe. One pipe is length is 2L, and the diameter also become D by 2. And when this divided, pressure head remains same. Now each pipe, how much, what will be rate at which liquid will flow? What will be Q dash here? So Q dash also I can calculate. Flow through one by Q dash will be again same formula. Pressure head remains same because it is connected like in this in the indicate pressure drop from one end to the other across length 2L. So P has remained same. Diameter has become D by 4 raised to power 4. 8 eta, in place of L, it has become 2L. So only thing what has happened, it is 2 to power 4 in the numerator and this another 2 in the denominator. So it is Q divided by 2 to power 5. That's the flow rate through one pipe. So if I make the diameter of the pipe half and length of the pipe double, so flow rate will drop by a factor of 2 to power 5. That will become smaller. That's the effect of this R of power 4 term here. But if I have connected four pipes here, if four pipes are connected in parallel, so if they are connected in parallel, see what does parallel connection mean here? In this case, parallel connection, if are connected to same pressure head, if pressure head remains same, is called parallel connection. This is very similar to resistance where voltage difference is same, is parallel, currents are different. Here also, when we collect various pipes in parallel, it means pressure difference is same, and flow rate will be equal to sum of the flow rate to all pipes here. So there are four of them. If I multiply by 4, it becomes Q divided by 2 to power 3. So flow rate, all through four pipes together will be 1 by 8 times of initial flow rate. So this is something very simple application of Boyle equation. And if I had, okay, what could be other variation of this? If I have other variation of this, we can also do something. They will give a question. What would happen if I connect a pipe of, we can have a different combination, series combination. What we connect two pipes of different diameters. In that case, what will happen if you look at this? If total pressure difference is delta P, here the pressure difference will be delta P1. Here pressure drop will be delta P2. So first part delta P1, delta P2. Only thing, sum of pressure drops have to be equal to delta P. And here what will happen in this particular case, when they're connected in parallel, delta P is same. Two are different in parallel connection. If pipes are connected in parallel. What happens if pipes are connected in series here? If pipes are connected in series, what would happen here? Q is same. Same wave, same liquid, whatever flow rate is happening, Q is same. Flow rate is same here. And delta P is shared. So if you know equation in case of current electricity, very similar, you can very easy to form equation. And you can do couple of questions, and this is really simple. I don't know whether it's there or not, but it's better to prepare few questions on this topic. Okay. Now coming to properties of solid. So solid have basically all the time we think that solids are something which